share screen. Okay, I'm not going to show you anything. We're going to go straight to the very beginning of this module. All right, so we'll start with Jacob. Jacob, what are the two drivers of reaction spontaneity?
It was enthalpy and entropy.
Good, but what is the direction of that driver? So I'll move on to Rithania now. So Jacob's mentioned entropy and enthalpy, Rithania. Are you trying to move to higher or lower enthalpy and entropy?
We drive towards higher entropy and lower enthalpy.
Very good, right? And Zinul, how do we quantitatively measure reaction spontaneity?
Is it with Gibbs free energy?
Very good. And Anne, what sign must the Gibbs free energy change have to indicate a spontaneous reaction?
Negative.
Very good. Akshita, what's an example of a reaction that is always going to be non-spontaneous?
Photosynthesis.
Very good. Good job. And going back to Jacob, what's an example of a reaction, Jacob, that is always spontaneous once you reach the activation energy?
Combustion.
Very good. Good job. And finally, we're talking about equilibrium systems. Rithania, what are the two examples of equilibrium? Just
Static and dynamic.
Very good. Right. Now, a bit of a harder question. Let's go to Zainul. Can you describe static equilibrium? When does that happen?
It's when like the reaction's occurring in the system, but like it stops, and then there's like no movement of like particles.
Very good. Good. I know you know it, but remember, in an exam, you're looking for specific buzzwords. If you don't have that buzzword, they're not going to give you the mark. So,
Okay.
Anne, what do you think are the buzzwords when the question asks you to define static equilibrium?
Well, it often goes to like completion. The forward reaction rate and the reverse reaction rate are equal, which is normally 0.
Good.
And it's sometimes considered irreversible.
Always considered irreversible.
Okay.
Those are the two features. Very good explanation. The two things I'm looking for when I say static equilibrium, it occurs in a system where there is an irreversible reaction and the reaction has gone to completion. As a result of this, the forward reaction and the reverse reaction rate are equal, brackets equilibrium, and equal to 0. Do you guys see how I use the word as a result of, or due to, or thus? When you use those words, you're explaining something, right? You're linking a cause to an effect, which is a definition of explain. Very good. Good. And finally, Jacob, what about a dynamic equilibrium? How would you define that?
So dynamic would just be where the reactants and products are basically always like converting. So like the products are converting to reactants, and then the reactants are converting to products at like a equal rate and then the constant rate, and the reaction would be reversible.
Very good. Good. Right. Very good. So that was the key points for that. And finally, a bit of not really an extension question, guys, but actually passing it on to you. To form an equilibrium, especially a dynamic equilibrium, is it possible for that to occur in an open system, or must it only occur in a closed system? Like I said, a bit of a harder question, so give it a go.
I think it could happen in a closed system.
Good. So equilibriums, dynamic equilibriums, only fall in closed systems. The reason for that, guys, is when you learn about this principle called Le Chatelier's principle. And the key gist of this principle is that equilibrium systems hate disturbance. They hate anything from the outside that will come in and interfere with what's occurring within the reaction system. When you open the system, aka matter can exchange between the system and the surroundings, there's always going to be a disturbance to the system. So it will never be able to properly reach an equilibrium, right? So equilibrium occurs primarily in closed systems, okay? A bit of an extension to that, if you have an open system, the closed system becomes the entire universe. What I mean by this is key example. When you open a new bottle of Coke, what happens to the drink when you open that bottle? What's the observation you make, Zainul?
There's a release of gas.
Good. Carbon dioxide gas. Now, carbon dioxide immediately goes and forms this equilibrium here. Carbon dioxide to CO2 aqueous. There's more reactions, but we're just going to keep it very simple for now. But as you all can understand, what happens when you open the bottle is that you change the pressure, right? Because now the bottle, which is high pressured, is introduced to the air, which is low pressured, right? And the bottle will get disturbed and it will try to recalibrate itself. And eventually, I think all of you can note when you taste Coke after days, it doesn't taste fizzy, it's not carbonated. That's because all the aqueous carbon dioxide has gone to solid. We'll talk about why that happened. But hopefully you're understanding that we disturbed that equilibrium in the bottle, right? And it was never able to form an equilibrium at the end because the reaction just goes completely in one direction because of that disturbance. Now, don't worry, we're going to go talk about the Chatelier's principle this lesson. Okay, good. Let's move on. Good job.
Well, I just had a quick question.
Yeah.
About the theory book. Is there any way to like download it so you can like
yes.
write on it? Yeah.
I was meant to mention this to the earlier class. I mentioned it to the earlier biology class, but same thing for us. The reason we can't download it is because of copyright and distribution factors. But what I can do, and I mentioned this to the biology students, so hopefully you'll remember this, is those of you who want to get the document printed, so it's all the students for biology. Again, can you guys just hit the raise hand icon if you'd like a printed copy of the chem notes? And actually, Tanya, good. All right, so all of us, good. In that case, what I'll need to do is I will need to go print the booklets for each and every one of you, and then staple and bind it. And then I would need you guys to pick it up from me directly, okay? Regarding picking up, I'm located in the city center most of the week, especially after school time, so you can come whenever you get the chance to come, or I can arrange, I know some of you live quite far from the city, you can message me and we can arrange for it to be picked up at a different time, place, etc. Okay, so that's going to be the plan. So you'll likely get your booklets either end of next week or the week after, and you may also get booklets for the next few modules as well. So I'll speak to your parents about that. So just let them know to check their emails tomorrow because I'll be sending out an email tonight regarding all of this and the logistics. Okay? Good. All right. Coming back to this content, let's jump all the way down to done all these questions. Let's move to where we left off here, which is talking about reaction rate time graphs. And I think all of you nailed this in the head in the question part of today's lesson where you mentioned the forward and reverse reaction rates are equal. And when that's the case, a system is at equilibrium, right? Now, the concentration time graphs are much higher yield, and I can almost guarantee to you it's going to either come up in your trial exams or your actual HSC exams, these concentration time graphs. Now, I want you all to think about concentration and time, right? We said at equilibrium, the forward reaction rate is equal to the reverse reaction rate. And I want us to focus on dynamic equilibrium here. Forget about static equilibrium, because like I told you, the rest of this module is all about dynamic equilibrium, whether you have a reversible reaction. Looking at the concentration time graph, do you think the concentrations are going to be equal? And do you think the concentrations are going to be constant at equilibrium? Any ideas? It's a hard question. You really need to think about this. So I'm going to give you all 20 seconds to digest what I just asked you. In a concentration time graph, do you expect the concentrations to be equal between the reactants and products? And do you expect it to be constant aka non-changing at equilibrium. And I want a y as to your answer. Can you hit the raise hand icon once you've got an answer? I need you all to think about this one. At school, you probably just learn and remember it, but I want you to work it out. Now, the best way to work out conceptual questions, everyone, is thought experiments, right? Whenever I'm asked a tough question, I go through a mind or a virtual thought experiment. This is a very interesting thing about the brain, right? You have infinite resources in here. Think the scenario out. So I'll give you an example. Let's say that I've got, and can you put it in the chat box? Can you just comment in the chat box? Reaction rate, do you think it's going to be, sorry, the concentrations, do you think they're going to be equal, and do you think they're going to be constant? While you're doing that, I'm just going to give you a little thought experiment. Nitrogen plus hydrogen gives you 2, 3. Okay. Let's initially say this. Good. All right, let's go to Jacob. Jacob, what do you think is going to happen to the concentrations at equilibrium? Do they have to be equal and do they have to be constant?
I'm not sure if this is right, but would the concentration be like the concentrations would be different amounts, but the rate would be equal? So it would be a constant rate.
Okay. Remember, you can't say rate with concentrations. I think you mean rate of formation, rate of destruction. But
Yeah.
Concentrations directly. So the concentrations, so Jacob's mentioned concentrations will not be equal, but they'll be constant. And let me posit it to Zainul. Zainul, why do you think Jacob has explained or identified the concentrations don't have to be equal? Why is that the case? You can give me a thought experiment.
I mean, I would say they would always be constant because if you have one, like let's say your ammonia reaction, if you have more ammonia, that disrupts your equilibrium. So you always want it to be like equal and constant.
Good. Do you want it to be equal? Do you want the concentrations between here, in this example, nitrogen, hydrogen, and ammonia, should all the concentrations be exactly the same?
Not necessarily just like constant, like stay like in equilibrium.
Very good. So you've all identified the correct answer. Now, the reason that the concentrations have to be constant is because when the forward reaction is equal to the reverse reaction, for every molecule that is formed, one molecule will be used up. So the net is always going to be 0, the change in concentrations, right? So that's very easy to explain. The slightly more challenging part is, why are the concentrations not equal? And to understand that, you just have to use a little thought experiment, right? I think the Haber process is a little too complex. I'm going to give you a very basic letter example. Let's say A combines to form B. This is such a simple reaction like pathway. This isn't even a proper reaction, right? Because something needs to add or delete. But just using this very simple reaction, let's say that 2 molecules of A forms, let's say 1 molecule of A forms 2 molecules of B, just to keep things very simple. That's our stoichiometric ratio, right? Let's say Anne does this experiment, and initially she puts 10 molecules of A. So that's initially in this container, right? Now, let's say that out of those 10 molecules of A, 3 molecules of A react to form B, everyone. How many molecules of B would we form? The 3 molecules of A are used up. How many molecules of B are formed?
Would it be 6?
Exactly, stoichiometric ratio, right? So in our cooking recipe, A is 1 part in our cooking recipe, and that represents 3 units. B is 2 parts, so it's going to be 6 that's made, right? So what's happened over time is we initially had 0 of B, 10 of A, and we subtracted 3 of A, and we added 6 of B. And let's say at equilibrium, that's the change in concentration. The equilibrium concentration of A is going to be 7. Equilibrium concentration of B is going to be 6. And they're going to be exactly constant after this point in time, because for every molecule of A that is formed, 1 molecule of A is used up. For every molecule of B that is formed, 1 molecule of B is used up. So what ends up happening is you see a graph that looks like this, where they start at random points. The starting points don't really matter because it really depends on, what the experimenter, in our case here, what was put in the container at time equals 0. Anything could have been put in. I could have started the experiment with 3 molecules of B and 21 molecules of A, and it would completely change all these numbers. The only thing that would remain the same is that at equilibrium, the concentrations would not change. So what you can all appreciate is right about after this time here, just vaguely drawing this line, right? Let me make it straighter for you. Yeah, the line's not exactly at the right place, maybe around here. Yeah, somewhere around there. You can see that the lines become perfectly horizontal, aka the change in concentration is 0. And you know that that is the point that equilibrium was established because the forward and reverse reaction rates are equal, right? So the key thing I'm trying to get across here is at equilibrium, forward reaction rate is equal to the reverse reaction rate, and concentrations are constant. That is the new point all of you are going to be adding in your definition of equilibrium. Concentration of all chemical species is constant or non-changing. This is a new piece of information you've just learned. Good. Now, very quickly here, can someone tell me what was present in the reaction vessel at time equals 0, just based on this graph? Akshita, what was present in the container at time equals 0?
Hydrogen and iodine.
Very good. And why do you say there's no hydrogen iodide?
Because it hasn't formed yet.
Yeah, very good, right? And in fact, if you just look at the graph, you can see the concentration is 0 at time equals 0. So there must be no hydrogen iodide yet. Okay. Now, if you guys were to have, on top of this graph, if you were to write or draw the reaction rate graph, what would it look like? It looks something along the lines this. Doesn't have to be at the same spot, so it could look like this, in fact. And it would use another axis, right? But after this point, the reaction rates would be equal. Initially, hydrogen and iodine, or in this case, the forward reaction rate would be high. The reverse reaction rate initially should be 0. I should have started from down here as well. And they'll equalize at a point. And it will use another y-axis, because this y-axis is concentration, and this y-axis would be reaction rate. Good. Good. All right. Any questions so far at all? Right. We still haven't gone through these graphs in detail because you'll be doing a couple of calculation questions and explanation questions from concentration time graphs. But I want you to put a little asterisk next to it because we'll come back to it when we do exam questions. Good. Now, we're talking about examples of chemical systems that are in dynamic equilibrium and in static equilibrium. And the first checkpoint is cobalt chloride hydrated and dehydrated. Now, I remember when I was a student and I saw this, the first thing I asked myself is, what does hydrated and dehydrated mean? Does it mean it's dissolved in water, non-dissolved in water? Does it mean it's chemically bonded? Zeno, what do you think? When I say a salt is hydrated, like cobalt chloride, what do I mean?
I would say it's mixed with water.
Being mixed and dissolved in water is different to being hydrated and dehydrated. In fact, can you all see this? Have a look at the reaction. You see a dot right here. The dot is telling you that the cobalt chloride is chemically bonded to water molecules, specifically 6 water molecules. I want you to remember this. To be hydrated means to be chemically bonded to water. Makes sense? You can remove it, you can dehydrate it. The word hydrated refers to chemical bonds that are formed between water and the salt. This will come up in exam calculation questions much later in the Year 12 chemistry syllabus. So for now, just appreciate that is what hydration means. Good. So this is the simplified equation, and on top you can see the complex equation. Now, a bit of an additional point. Does anyone know what we call this when we represent a metal that's bonded to water, has these square brackets, and has charges and numbers and all this weird stuff? Essentially, guys, what you're seeing up there is just cobalt, right? It's the same thing. It's cobalt bonded to 2+. This is just a more detailed explanation of exactly what's happening to cobalt. Does anyone know what we call colored chemical species of metals? An example would be copper is always blue. Cobalt in this case is pink. Does anyone know what we call colored metal species in water? Starts with C. Complexes. Okay? So whenever you have a metal that's combined to water and has a charge, you call that a complex. And so the reason why certain salts give colored solutions is because they form complexes. The key thing I want you all to understand is every time a metal dissolves in water, if it changes the color of the water, it has formed a complex, right? So if I told you iron 2 is green, iron 3 solution is a yellowish brown solution, you would immediately go, since it formed a colored solution, it is a complex. Now, we're not going to talk about what makes up a complex for this module, so don't worry about that. All I need you to do is be able to point and say that is a complex, okay? And we'll add on that detail later in the course. Good, so as long as you understand why it looks funky like that, okay? Showing you that it's a complex. Now, coming back to this, what you see is cobalt ions, that's essentially what they are, that have been hydrated or chemically bonded to water, combine to chloride ions to form cobalt chloride. And when they form cobalt chloride, you get a blue color change. It goes from pink to blue. Now, the reason the HSC syllabus wants you to look at this system is because you can play around with it. You can start changing the temperature, you can add certain ions, and you will see the color in that beaker will change in front of your eyes. Can you hit the raise hand icon if they've done this experiment already at school? Good. It's quite interesting, right? You increase the temperature, it will change the color. You add sodium chloride, it will change the color. You add more water, it will change the color. It won't just dilute the color, it will literally change the color of the solution. That's real life happening, and you'll be using a certain scientist's principle to explain why it's changing. Okay, good. So this is a basic reaction. Now what you see is you see heat on this side of the reaction. And what is that telling you about the forward reaction? Is a forward reaction endothermic or exothermic?
It's endothermic.
Very good, right? Because it's telling you, the way I remember this, is if heat was being released as a product, we say it's exothermic because it's releasing heat, right? In this example, we can see heat's on the left-hand side, which means it's being used up as a reactant. So we say it's endothermic. A little tiny thing that I like doing is if triangle H is negative, aka it's exothermic, you can kind of add it to the end of the reaction like this. And this is going to help you out a ton when you're answering questions to me about how the equilibrium will shift when we disturb it. All right, so remember this. When you have enthalpy that is negative, when you bring it into the reaction as an actual product or reagent, you change the sign. See how it went from negative heat? So if it was negative 92 kilojoules per mole, when you bring it into the equation, I'm just going to write positive heat, change the sign. Okay, good. And similarly, if triangle H was positive heat, everyone, okay, it was, let's say, positive 32 kilojoules per mole. When you bring it into the reaction, you'll write negative heat here. And remember, you always want to have positive heat in a reaction system, right? You want it to be written as plus heat. So then what you can do is you can bring it to the other side of the reaction like this. Now it will be plus heat. And now it's being represented that this is an endothermic reaction. It's using up heat, right? This is just a way to think about enthalpy that will help you a little bit more in understanding how temperature will disturb an equilibrium. Okay? Does that make sense to everyone so far? Good. It'll make much more sense when I ask you to explain in terms of Le Chatelier's principle. But very good for now. Good. So that's one equilibrium system, and it's endothermic. Don't worry about the method. You just literally add the two salts in a beaker and you see these colors. That's literally everything. Okay. Now, to explain the rest, we need to talk about Le Chatelier's principle. And Le Chatelier's principle is going to form the dogma, or the most important part of this module. Okay? Every question after this point is going to be based on Le Chatelier's principle. Now, can anyone tell me what Le Chatelier's principle is? Anyone learned it at school?
Is it when there's a change imposed on the system, it like rearranges to form a new equilibrium?
Good, very good. Now, Anne, when it rearranges to form a new equilibrium, is it trying to oppose the change, or is it trying to amplify the change?
Oppose the change.
You know what's really interesting is, for those of you, can anyone raise their hand if they do all three sciences? No. Okay. Well, I did all three sciences, and I noticed something very interesting, which was in biology, the human body loves or always wants to counteract changes, right? If you increase your body temperature, you feel really tired. The chemical reactions in your body slow down. You sweat to lower your heat. When it's very cold, you shiver. So skeletal muscle contraction generates heat and you raise your body temperature. The human body is always counteracting change. Now in chemistry, Le Chatelier's principle is exactly the same thing. It's chemical reactions trying to counteract any change imposed upon them. Okay? And who does physics? Can you hit the raise hand icon? Good. Zeno, what is Faraday's law? Have you learned Faraday's law?
No, I don't think so.
Okay. But Faraday's law is really interesting because it's how electricity is made today. The reason your lights are on, the reason your tablet is, or your PC is glowing in front of you, is when you move a magnet around a wire, you disrupt the magnetic field around the wire. And what the wire does is it creates electricity that creates its own magnetic field that's going to counteract the magnetic field imposed on it. Now, for those of you who don't do physics, you don't need to memorize this or learn this, but I just want you to get the idea that counteraction of change is a universal part of nature, whether it's chemistry, physics, or biology. The Chatelier's principle is one example of this. Okay? Now, I'm going to give you the dumbed down explanation of Le Chatelier's principle, and then I'm going to tell you exactly what you need to say in your exams to get full marks, because those are two different things. In a dumbed down sense, Le Chatelier's principle, first of all, only applies to dynamic equilibriums, those that have a reversible error, right? And what Le Chatelier's principle says is whenever a disturbance is placed on the system, or this reaction, the reaction will change itself to partially counteract the disturbance. Okay, it's the same thing in biology, right? If you increase your thermostat or decrease your thermostat to 18 degrees, you're going to be shivering, but your body temperature is not going to return back to normal. It'll partially counteract the lower temperature. In the same way, Le Chatelier's principle, I want you to write this down, it's a partial counteraction of disturbances. Partial, very important word, of disturbances on a chemical equilibrium. Now, how can we disturb an equilibrium? How can we annoy this chemical reaction here? Let's go to Zainal. What can I do to disturb this equilibrium?
You could decrease or increase the temperature.
Very good. So one thing we can change is temperature. There are literally only three things you can do. So Zainal's already got one of them. What's another one, Zainal?
Changing the concentration.
Very good. So I can take some, some of these molecules out. I can add some of these molecules. Very good. So concentration. And what's the last one? The last one does not apply to this equilibrium, but it will apply to those that have gas molecules forming?
Pressure.
Very good. Pressure and whenever you say pressure, what's the other thing you need to say?
Volume.
Very good, right? So it's the ideal gas law quadrant. PV equals nRT. Tells you pressure, volume, and temperature all related to one another. But good. So these are the 3 ways you can disturb a chemical equilibrium. I want you all to realize, do you see how I did not say catalyst? I did not say surface area. This is different to particle collision theory, so do not mix them up, right? So technically they're very linked, but I'll explain that to you much later. But for now, I just want you to appreciate the factors that affect an equilibrium are similar to those that affect reaction rate, okay? But they're slightly different as well. Okay, so there are 3 things that can disturb an equilibrium. Very good. Now, let's talk about an exam answer for the Chatelier's principle. Now, I would highly recommend, don't worry about reading and memorizing this, right? But when you say it out loud to yourself enough times, it'll just stick into your head. Like, I don't study HSC Chemistry. It's been seven years. The reason all of this sticks is because I'm teaching it to you guys. So I want you to say it out loud, say these words out, teach your friends, and I can promise you that is the best way you can level up in your content for HSC Chem. Okay, put your hand up, answer questions, teach it to yourself, teach it to a friend. It'll help you more than it will help anyone else. So the exam definition of the Chatelier's principle, I'm going to say it. Don't worry about writing it down as fast as you can. It's in these notes. I'm just going to say it for now. I want you to just maybe jot down what are the key words you hear, and I'll say it again, right? So Le Chatelier's principle states that when a dynamic equilibrium is subject to a disturbance, it'll partially counteract that disturbance to restore its equilibrium position. Okay, so the key words that you heard there was dynamic equilibrium, disturbance, and partially counteracting the disturbance to create a new equilibrium position. Right? Those are the 4 parts of my template answer. And now let me show you the written one, just so we don't. I know we like having written explanations. Where is it? Here you go. Okay, this is your exam answer. It's on page 48 for all of you who should have exam access to the notes, right? The system in dynamic equilibrium subject to a change in conditions, it'll partially counteract the change. It'll form a new equilibrium position. It'll return to equilibrium eventually. Good. Any questions about the definition?
I have a question.
Yep.
You know how you said new equilibrium? What does the new mean?
Very good question, right? So what new means, we need to see a graph to really understand this, actually, though. So let me just pull down and see if we've got a graph for us. These notes. There you go. Okay. So when we say words like equilibrium position or where the equilibrium is located, we're just talking about, if we're talking about I'm going to write products and reactants, right? Reactants on the left-hand side, products on the right-hand side, right? I'm sure you all know by now, whenever we say the word equilibrium, the forward reaction rate is always equal to the reverse reaction rate, right? Sometimes you will see words written in textbooks like the equilibrium lies to the right-hand side, or the equilibrium position is to the right. Now, some students might think, okay, this means the forward reaction is more than the reverse reaction, right? That is not the case. The definition of equilibrium is grounded in this. What is the other point, Anne, that I mentioned that you must say now for definition of equilibrium?
That the concentration is constant.
Very good, right? So when we say that an equilibrium lies to the right or a new equilibrium position has been maintained, just have a look at this graph for me, everyone, right? This is a system that's all happy, in equilibrium. doing its thing, and then suddenly someone comes along, disturbs the equilibrium. They heat up the system. Suddenly all the gases start changing their concentration because they want to counteract this. They want to lower the temperature of the system. So they will change, and eventually, can you all see, they re-establish equilibrium sometime around here at time 2, right? And I know that because the concentrations are all constant, just as Anne said, which is one of the key definitions now of equilibrium. But what do you notice? Are they all in the same concentration that they initially were, or are they all at different concentrations now? Everyone? Same or different concentrations?
Different concentration.
Different. So now what we say is the equilibrium position has changed, meaning the concentrations at equilibrium are now different. They're still at equilibrium, they're at a new equilibrium, but since the concentrations are different at this new equilibrium, we say the equilibrium position has changed. Now, if you look at these chemicals, right, what are the gases? It's SO2, SO3, and oxygen. So if I combine SO2 with oxygen, I will get SO3. I'm not going to balance it. We don't need to do that right now. But what can we all appreciate, everyone? What happened to the concentration of my product, which is SO3? Did it go up or did it go down? Jacob, what do you see is happening?
Decreased.
Very good. It's decreased, right? So this has gone down. And what we can see is at the same time, SO2 and O2 have gone up. So what you could say to describe what has happened is the equilibrium has now shifted to the left, or the equilibrium position now lies to the left. What that means is now there is a constant higher concentration of my reactants, which are on the left, and a constant lower concentration of products, which are on the right. Actually, has the reaction rates changed?
No.
They're equal. They're always going to be equal. The forward reaction rate is equal to the reverse reaction. That is the definition of equilibrium. The thing that has changed is the concentrations at equilibrium are now slightly higher for the reactants, lower for the products. So we say it lies to the left, lies to the right, or we say a new position has been established. So that's what that word means. I had to explain it to this depth, guys, because a lot of students don't know what they're saying when they say an equilibrium position, or it lies to the left, lies to the right. It's often difficult for us to conceptualize, but does anyone have any questions? Jacob, question?
Yeah, so when the equilibrium is shifted to the left, does that mean that more reactants are formed then? Is that why the concentration increases?
Good, exactly what you can see there, right? So temporarily, Jacob, the reverse reaction was favored. But between this time and this time, the reverse reaction was favored. The reverse reaction was greater than the forward reaction. As a result, we made more of this. Does that make sense? But as soon as we hit time...
So does that mean the products have to decrease then?
Yes, exactly.
Okay.
You can see that, right? You can see that SO3 has decreased from this value here to this value.
Oh, okay.
Good. Yeah. So what's happened temporarily between this time and this time is a reverse reaction was favored. The reaction went a net direction of to the left. We made more of this. And then it hit equilibrium again, aka the forward and reverse reaction rates became equal again. Good. Good. We're jumping a little bit here, but I only wanted to go through this because actually they asked the question. But we're going to now jump back to the main key points. And when we come back down, it'll make a lot more sense. But does anyone have any further questions at all? Please ask away. Good. All right. Good job. So now that you understand this, let me actually explain how you think about it. Because all I've said is there's a disturbance and the system panics and it tries fixing itself. But I never gave you a way to think about it, right? Which is what I'm going to teach you now. The next minute of what I'm going to teach you is going to be the most important thing you learn for Module 5 HSC Chemistry. I want you to pay attention to this. Every single exam question in Mod 5 can be answered, especially about the Chatelier's principle, can be answered by what I'm about to teach you. Let me just go up to the cobalt chloride question here. Okay, so pay attention to this. So no matter how hard the Le Chatelier's principle question is, if you apply what I'm about to teach you, it'll be easy, piece of cake. Okay. The way you think about the Chatelier's principle is you ask yourself 3 questions. Question 1, question 2, question 3. The first question you ask yourself is, what was the stimulus? Meaning, what disturbance did we apply to this reaction system? Okay. Now, the disturbance must be one of the 3 points which we said above, right? I know it's written there, but Rithani, can you just repeat it to us? What are the 3 factors that affect equilibrium? Rithania? 3 factors. Spoken about temperature. What are the other 2 factors that affect equilibrium?
Pressure and concentration.
Very good. So concentration, and then pressure and volume as well. Very good. Right? Okay, so you always need to define it in terms of that. Okay, I don't want you to tell me, oh, substance X was added, substance Y was removed, the vessel got bigger. I want you to tell me the concentration of substance A went up, the concentration of substance B went down. Since the vessel was increased in size, the pressure of every substance decreased. So I want you to always explain in terms of T, C, or P/V. Make sense, everyone? The next thing I want you to ask yourself is, what is the exact opposite of that stimulus? Right? So let's go through an example, right? An example will help you answer this question. Let's say that I added, sodium chloride to this test tube, right? To a container containing this system that you see here. So look at the equation that I've boxed out, okay? Now, and when I add sodium chloride, what have I changed? Have I changed temperature, concentration, or pressure/volume?
Wait, what equation are we looking at?
The first one. Don't worry about it's the same equation, but the first one is easier to interpret when it's written down for you.
Okay.
So when you add sodium chloride to a beaker containing equilibrium 1, have you changed temperature, concentration, or pressure/volume?
Concentration.
Very good, right? Now everyone can appreciate when sodium chloride dissolves, it's going to release sodium and chloride. Now, Zainul, is sodium in the equilibrium? Do you see an Na written in equilibrium 1?
No.
No. So the Na is useless. It's not going to do anything. But what about the Cl minus? Jacob, do you see a Cl minus in this equilibrium?
Yeah, it's on the side of the reactants.
Good. So what's going to happen to the concentration of chloride, Jacob? When we add
well, the concentration would increase.
Very good, right? So Jacob's correctly identified the stimulus is an increase in the concentration of Cl minus. Now, Zainul, very simple question. What is the exact opposite of that stimulus? That's it. Just literally write the exact opposite of the stimulus, right? Which is a decrease in concentration of Cl minus.
Okay.
Okay.
Well, how come it doesn't increase on the product side?
Good question. That's because this is a unit together, right? When you add Cl by itself, it can't just go and join to more cobalt chloride.
Right.
You know
Okay.
what I'm saying? It can't form cobalt Cl6, for example, right? So the first thing the Cl does, it combines with, it's going to participate here, and then it will form more of this, which is what.
Oh, okay.
Yeah. Good. Good pickup, right? You do see Cl on both sides, so it's very important to identify which side it's affecting. Okay, but good. All right, so coming back to this, the exact opposite is decreasing the concentration of chloride ions. Now, finally, Rithanya, let's go to Akshita because I already asked Rithanya. Akshita, what direction must I go to achieve this opposite effect, which is decreasing the concentration of chloride ions? Should I favor the forward reaction and go this way, or should I favor the reverse reaction and go this way?
Reverse reaction?
Let me help you out, right? Wherever this arrow is pointing, that's what you're going to make more of, right? So actually, when we favor the forward reaction, the arrow is pointing to the right-hand side. What do we make more of?
Cobalt chloride and
Good.
water.
Very good. And where the tail is, that's the negative, right? So that's what we make less of.
Yeah.
So we make less chloride ions, we make less cobalt, which is hydrated. Yes? The same way, if I go the reverse reaction, actually, wherever the arrow points, that's what I make more of, right? So I make more chloride ions, I make more cobalt ions, but what decreases?
The cobalt chloride.
Very good, right? So remember, our goal here is we want to decrease the concentration of chloride. So which direction would you want your arrow to point to decrease the concentration of this specific ion?
Forward reaction.
Very good. So you would tell me the forward reaction is going to be favored to use up the concentration of chloride ions. So the final question you ask yourself is, what direction must you go to achieve the opposite, to achieve question 2? Okay, and this is summarized in my acronym, which I always ask students, which is SOD, stimulus opposite direction. So from this point onwards, every single Le Chatelier's principle question you do, you're going to be asking yourself, what is a stimulus? What is the exact opposite of that stimulus? And finally, what is the direction you will go to achieve that exact opposite? Good. So in summary, if you add more sodium chloride, everyone, which direction is the equation going to go? We said it's going to go to the
Right.
Very good. And so what color will this beaker become?
Blue.
Blue. Yeah, blue or pink, as you said, blue. Exactly. So it'd be very interesting. When you add the colorless sodium chloride, the beaker will change from pink to blue. And now you know why. It's due to Le Chatelier's principle and the dynamic equilibrium trying to partially counteract change. Now, here's a final question to test your knowledge, right? If the initial concentration of chloride ions is 1, let's say it's 1 millimoles per liter. Actually, you don't even need to know that. Let's say if I increase the concentration of chloride ions by 1 millimoles per liter. So I added enough sodium chloride. I shouldn't even say millimoles. Let me just write moles. 1 mole per liter, right? If I increase the concentration of chloride ions by 1 mole per liter due to the addition of sodium chloride, when this equilibrium shifts to the right, how much will the chloride ions decrease by? Will they decrease by A, greater than 1 mole per liter? Will they decrease by B, equal to 1 mole per liter? Or will they decrease by C, less than 1 mole per liter? And any ideas?
Would it be B?
Equal?
Yeah, equal.
So if I add 1 mole of sodium chloride, you're saying the equilibrium will shift to the right so much that all of that 1 mole is used up?
Yes.
Okay, good thought. Any other ideas?
Or would it be less to equal it out?
If it was less, it wouldn't equal out, though. Do you agree? If it increased by 1 mole per liter and it decreased by 0.5 moles per liter, the net change is going to be an increase by 0.5. Do you agree?
Okay. So, I mean, I don't know. I think I'll just stick with B for now.
Okay. Jacob, any ideas?
Would it be C just because of the molar ratio?
No, I think we're thinking too hard. What did I tell you all was a very important word in Le Chatelier's principle? The P word.
Partially.
Partially. Right? Le Chatelier's principle only partially counteracts change. So if the change was an increase by 1 mole per liter, we only partially counteract it. Does that make sense to everyone? So we'll never ever completely counteract it and decrease by 1 mole again, aka completely cancelling it. So +1 minus 1 minus 1 is going to be 0, right? We're not going to do A. We don't counteract and then take some more off. That's not Le Chatelier's principle. Le Chatelier's principle is a partial counteraction of change. So when we add the sodium chloride, only some of that chloride ions are going to be used up, but the net effect is still going to be a small increase in chloride ions. Le Chatelier's principle can't completely counteract this increase by 1. It'll counteract it by decreasing it by less than 1. And does that make sense?
Yes, so if it's taking less, and so it converts less than 1 mole to cobalt chloride.
Correct. That's right.
And then will some of it still stay on the chloride ions side?
Exactly. So there'll be a net. So let's say because of Le Chatelier's principle, let's say it was increased by 1 mole per liter, and then due to Le Chatelier's principle, it decreased by 0.5 moles per liter. That means for every 1 liter of solution, 0.5 moles of chloride ions are still present on the reactant side. Yeah. Okay, that's what partial counteraction means according to Le Chatelier's principle. Whatever change I impose, if I increase the temperature of the system by 5 degrees, the equilibrium will shift to decrease the temperature, but by less than 5 degrees. If I increase the pressure twofold, Le Chatelier's principle, the system will shift to decrease pressure, but by less than twofold, partially counteracting the change. Is it starting to make sense to everyone?
Yeah.
Good. As you guys do more questions, it'll make more and more and more sense. But very good. All right, we've hit the 5 o'clock mark. But what I get you all to do, just absorb everything you just learned. The SOD framework, I just say SOD, right? So every time I ask you a Le Chatelier's principle question from now on, you need to tell me what is a stimulus, what is the opposite, what is the direction the system will go. Okay? Very good. This lesson is going to get a lot more fun because I'm not going to be doing as much talking from now on for the rest of the lesson. Hopefully, I want it to be me asking you questions and you guys applying this framework to multiple different question types, so it starts to make a lot more sense. Good. All right, I'll see you all at about 5:05, okay? Okay, when you're back, you have the raise hand icon, and we would jump into things. Good. Good. All right. Okay, let's go to your next question is going to be, let me rub all this out. What would happen if I heated the solution? What color would it become? So again, the same equilibrium. Look up here. I want you all to think for about 20 seconds. One thing you've all learned is you've learned how to answer the question, but you haven't learned how to word your answer, which is what I want you to focus on now, right? When I ask you for your answer, I want you to give me as much of an exam-style answer as possible. You can't say, the stimulus is this, the opposite is this, the reaction direction is thus this. That doesn't make sense, right? You need to code it into an answer. For example, let me answer the first question again, right? I would say something along the lines of, the addition of sodium chloride would increase the chloride concentration. The system would thus shift to the right-hand side to partially decrease the chloride ion concentration and re-establish an equilibrium position. Brackets, LCP. That would be an exam answer, right? So when you've got your exam answer, say it out loud. You've got your exam answer ready to say it verbally, hit the raise hand icon. Zainul, are you ready? Raise. Give you all about 20, 30 seconds, then I'll ask someone. Bethania, what's your answer? Exam answer. Explain the effect of increasing temperature on the reaction system.
I said as the temperature increases, the reaction shifts to the right-hand side, changing the color to blue, pink from blue.
Good. All right. That was a very good first, question answer attempt. Good job. Got the answer right for the direction it travels. What would you add? Now, let me ask people consecutively. Akshita, what would you add to this answer?
So she mentioned all the dot points, but she didn't link it like cause and effect.
So how would you do it? What's your answer?
So instead of saying like just the point, so I would reword it saying that it would change to pink because of an increase, the temperature increases, therefore there'll be like a reaction. I'm not sure what I would say personally, but
Okay, good. Do you see the difference now, right? I know you all know the answer, but then getting it to full marks in an exam is a whole other game of exam technique, which is why for any science subject, you can break it down to, do you know the content, which will take you to about 80%, the last 20% to get a band 6. It's all about how do I answer the question to get 4 marks? And just give me a word. What other words or terms could she have used in her answer?
Like favors or direction?
Good, kind of. I'm looking for another word. Zainul?
link it to the principle?
Good. I don't think I heard Le Chatelier's principle. Correct me if I'm wrong, Britannia, but according to Le Chatelier's principle, due to Le Chatelier's principle, is so important. Jacob, what else could you mention?
That equilibrium is reestablished and that it's partially like minimized or partially
Good.
counteracts.
Good. The last thing, which I haven't heard, is endothermic or exothermic. Whenever you're talking about temperature, you need to tell me whether it's endothermic or exothermic. So let me show you my exam answer to this, right? I want you to jot down all the keywords. Okay, so I would say something along the lines of an increase in temperature would cause the system to shift to favor the endothermic reaction. What are we doing here? Sorry, not endothermic, the exothermic reaction. Okay, so I'd say something along the lines of an increase in temperature would cause the system to favor the exothermic reaction to partially counteract the change. As the forward reaction is endothermic, the reverse, sorry, let me clarify this. So coming back to this, my stimulus that we mentioned was an increase in temperature. Our goal is we want to do the exact opposite. We want to decrease temperature. So we are going to be shifting to the right-hand side. Let's go to Zainul. Is the forward reaction endothermic or exothermic for this?
That's endothermic.
It's endothermic, right? Very good, right? So you're going to be favoring that forward reaction to use up the heat. Very good. But then we are going to be shifting to the right-hand side. Good. So your answer would sound something along the lines of, as the forward reaction is endothermic, an increase in the temperature would cause the system to shift to the right to partially decrease the temperature and reestablish equilibrium, right? So key things I'm looking for with a temperature answer is identifying the forward reaction as either exothermic or endothermic, right? And then linking the direction, linking that to whether you're increasing or decreasing temperature, right? So in this case, the forward reaction will thus be favored in order to decrease temperature. Direction versus temperature. And then finally, the whole partial counteraction and re-establishing equilibrium. But the key thing, guys, with the temperature question as you're getting here is you must tell me, sorry, screen stop sharing. Give me 1 moment. Good. The key thing is you need to tell me whether the forward reaction is endo or exothermic. You need to be using those terms. Good. Jacob, question?
Yeah, because it shifts to the right, does that mean that more products are going to be produced?
Exactly. So what
So
color?
wait, wouldn't it go blue then?
Exactly. So when you
Oh,
increase
okay.
the temperature, you would see the solution become more blue.
Oh, okay.
Yeah, very good. So that's why you guys are studying this equilibrium. It's a very simple colored equilibrium that's going to show you in front of your eyes that Le Chatelier's principle is true. It's ingrained in the chemistry, right? It's not just stuff you're learning on paper. Very good. Good. And question?
So can I just clarify? So the forward reaction would be favored because it's an endothermic reaction, and it's partially counteracting the heat that's been added or like increased.
Exactly. That's why I like you guys writing heat on the left-hand side or the right-hand side, because then you can treat it like a reagent, right? You can ask yourself those 3 questions. So, for example, if it's endothermic, you'd say triangle H is equal to positive 30 kilojoules, right? So you go, okay, triangle H is positive 30 kilojoules, which means triangle H is positive heat. If I was to bring it into the reaction, it'll be negative heat on the right-hand side, but negative heat doesn't make sense. So I'm going to switch it again to this side. And I treat it like an actual substance, like you treat oxygen, water, etc., right? Then you ask yourself those 3 questions. What was the stimulus? It was an increase in heat. What is the opposite? I want to decrease heat. So which direction would I go? I'd go to the right-hand side, where I'm using up this reagent, which is heat, to counteract this stimulus. That's how you should be thinking about it. Does that make sense, Anne?
Yeah, thank you.
Good, good. All right, we're going to do a couple more of these questions because I want us to get very confident with this stuff. Okay? Good. All right, so let's say here you go. Explain the effect of adding silver nitrate, which precipitates chloride ions to the color of the equilibrium. Okay, I'm going to give you all about 30 seconds, then you're going to verbalize it to me. You can write down whatever you like, but I want a verbal answer. If you can say it, because you think and you talk much faster than you write, if you can say it, you can easily write it in an exam, right? So the effect was adding silver nitrate, which is going to precipitate with chloride ions and form silver chloride. When you get your answer, your exam answer, can hit the raise hand icon.
What was the question?
What's the effect of adding silver nitrate to the equilibrium? Anyone got an answer yet? Jacob, start us off. So with any Shadley's principal question, what are the 3 questions you ask yourself?
So the stimulus,
Yep,
the opposite, and then the direction.
good. So give it your best go. What's the stimulus that's happening?
So the stimulus, would it be an increase in concentration
Of what species?
of, well, you're adding silver nitrate, right?
Yep.
So, and that's going to react with the chloride ions. So wouldn't that mean that there's more reactants?
Close, but I want you to tell me, and what's the state of the chloride?
Oh,
in-
it's a solid.
Good, good. So Jacob, you've picked up. The chloride in the system is aqueous, but the chloride that we make uses up that aqueous chloride to make solid AgCl. So when something is solid in a solution, it's kind of being locked away. It can't participate in the reaction when it's a solid, right? So then what is the stimulus? Do you see how, even though the 3 questions are very simple, understanding the stimulus is sometimes a bit confusing. So what is the stimulus if you had to word it again, Jacob?
So we're actually decreasing the concentration of the chloride ions.
Exactly.
Okay.
Good. So I will get, actually have to finish it off for us. So Jacob's identified the stimulus correctly. What's the opposite and what direction will we go?
So since he said decrease, so we want to increase the concentration.
Good.
And to increase the concentration, we would go from right to left.
Right to left. Good. Very good, right? We want to achieve that opposite, so we're going to point towards the chloride to increase it. So you're going to go to the left-hand side, okay? For your exams, I don't want you to say shifts from right to left. I just want you to say shifts to the left, okay?
Yeah, okay, cool.
Now, finally, I will get Rithania. I want you to give me an exam answer. So they've helped you all out with the 3 steps, Rithania. What's the exam answer to this? What does the addition of silver nitrate do to the equilibrium?
The addition of silver nitrate added to the reaction decreases the concentration of chloride ions.
Good. Keep going.
Therefore shifting the reaction to the left-hand side.
Good.
To encounter partial.
So to partially counteract, that's what you're looking for? Yep, keep going.
Yes.
According to who? What principle is this?
According to Chatelier's principle.
Very good. You must say that part. If you don't say LCP, you need to say the full word, to Le Chatelier's principle. And then if you mention to it or refer to it multiple times thereafter, you can call it LCP. It's a very small exam, like things examiners prefer, but they want to see you write the full name, according to Le Chatelier's principle, right? I always like to start with according to Le Chatelier's principle, right? It just starts your answer off well. So my exam answer would be something along the lines of the addition of silver nitrate will precipitate and decrease the concentration of chloride ions. According to Le Chatelier's principle, when the concentration of chloride ions is decreased, the system will shift to the left to partially increase chloride ion concentration and re-establish equilibrium. As a result, the solution will change from a blue to a pink color. I think that's the final thing which we didn't mention as well. Now, this is a skill you'll build as you do more and more questions, but I highly recommend you say your answers out loud and then you write it down. It's a very powerful technique because when you say things, when you use words every day, it embeds or ingrains in your memory and your understanding. You might realize, I notice this in medicine a lot, when there's fancy long words, if I don't say the word, I never know what the word is. But the second I start saying it out loud and explaining it to myself, the concept starts to make sense. You identify gaps in your knowledge that you wouldn't have if you just kept it in your brain as well. Good. And question?
I was going to ask, in your exam answer, do you talk about the opposite, or is that just more of like a mental thing?
That's more of a mental thing.
Okay, so you just say the stimulus and the direction will go to counteract the change.
That's literally it, yeah. When concentration of chloride ions is decreased, the system will shift to the left-hand side to partially increase. I kind of add that at the end. The system will shift to this direction in order to, and I'd say the opposite. So the template to Le Chatelier's principle is quite literally, when stimulus occurs, according to Le Chatelier's principle, the system will shift to direction in order to achieve opposite. And then you'd say, and re-establish equilibrium. That would be a good template answer to always say for LCP, right?
In majority of the equations, do we have to talk about the color change?
No, because the majority of the time they're not going to be a color change, right?
Okay.
There'll be a lot of systems where there's some where there's a color change. There'll be some where it's not a color change, but you just need to identify what happens or what direction it goes, right?
Okay.
Yeah. Good. If there is a color change, you must refer to color change because I want you to relate it to the macroscopic change. Good. Very good. All right. And have a look at this, right? If you look at this beaker, does it look like everything's colliding and reactant is going to product and product's going back to reactants, everyone? No. It just looks like a pink colored solution, right? This is macroscopic constancy. When something is in equilibrium, it will not change color. It will not appear as if things are changing. But the second you disrupt equilibrium, you will see a change in the macroscopic constancy, right? Because remember, that was one of the features of an equilibrium. Very good. All right. Now, this is your challenge question. Explain the change that would be observed if more water was added to the equilibrium system. I want you to think really hard about this. When water is added to the equilibrium system. This is the one that even tends to get students off. Even the ones that are about to sit the HSC exams. Just think about what's the mistake that students might make for this kind of question. It's a little bit hard. I don't want you to be too precautious and not answer it, but just jump straight into it and I'll identify what the misconception is, right? So it should that if water is added to this equilibrium system, what is a stimulus?
The first thing that's coming in my mind is you saying the chemically bonded water, like, you know how you said chemically bonded and it won't like affect anything. So I don't know if it's concentration.
Okay, don't worry about this specific one. So it's not going to be a pitfall for this equilibrium. What I'm looking for. So don't worry about that water on the left-hand side. That's my little tip for you. Forget about that water.
Okay.
So what would the stimulus be?
So the concentration?
Yeah. So concentration of what and how is it changing?
Concentration of water increasing.
Okay. Let me ask you all this. If I gave you all a bit of water in your hand, right? You put your hand up to me. You just dropped a bit of water in your hand. And I asked you, what's the concentration of that water? Would that make sense to you?
No. Wouldn't it be volume?
Volume, yes. But remember, when I say pressure and volume, that only relates to gases. Zainul, can you see any gas?
Okay, no. Okay.
No. Good, very good thought. Very good thought. But like I said, pressure volume is specific to gases. If it doesn't have gases, you know, making the vessel smaller or bigger is not going to change the equilibrium, right? So do you all agree, solids and liquids, if I ask you their concentration, that makes no sense. If I gave you gold and I asked you what the concentration of gold was, it wouldn't make sense. You'd just tell me the density. You'd tell me the mass of gold in a volume. And if I want to increase the number of moles of gold in my hand, the volume of gold would proportionally increase as well. So what I'm trying to say here, concentration of solids and liquids, when you increase the number of moles, the volume will proportionally increase. If I give you more moles of water in your hand, the volume of that water would proportionally increase to keep concentration constant. So a huge point that you cannot forget, and this is how they'll trip you up in exam questions, right? They're not going to give you easy, straightforward questions like the first question we did. They'll give you questions like the silver nitrate question where it precipitated and it decreased something, or they'll ask you a question where they change the concentration of a liquid or a solid. When you change or add or remove liquid or solid, you are not changing concentration. So the answer usually should be no change. What I mean by that is if I had X that was a solid, and if I said, and what's the effect that would happen if I added 2 more grams of X to this equilibrium system, what would you tell me?
I would usually say there was an increase in concentration.
Good, which you would initially think that, but now you know, since X is a solid, you can't increase its concentration, right? If you add 2 more grams, you increase the volume as well. The concentration will be constant, right? So then your answer would be that the increase in the mass of X will not affect concentration and it will not disturb the equilibrium. There will be no change to the equilibrium position. Does that make sense? Because we haven't changed concentration, we haven't changed pressure volume, we haven't changed temperature. As a result, we have not changed the equilibrium. But it's a caveat with water. Why is it a caveat with water in aqueous systems? When I add more water, sure, I'm not changing this water here because it's a liquid. But what am I changing when I add more water?
Don't you dilute the?
Very good. So, Rithania, what would happen to the concentration of all the aqueous species?
It would go down.
Very good. So this would go down, this would go down, this would go down. So the stimulus is a decrease in concentration. And if I asked you what, you would say of all aqueous species. What is the exact opposite of that, Jacob?
An increase in concentration.
Good. All right, of all aqueous species. Now, how many aqueous species do we have on the left-hand side? And how many aqueous species do we have on the right-hand side?
Two on the left, one on the right.
Yeah, you'd think that, right? But you need to also account for the stoichiometric ratio. Because every time you cause one round of the forward reaction to happen, you use up 5 moles of aqueous species and you create 1 mole of aqueous species. Do you agree?
Yeah.
So what you need to do is you need to add up the total number of moles on the left-hand side that are aqueous. So in this case, it's 1 plus 4, and that would be 5. And on the right-hand side, you'd add up the total as well. And that would just be 1, because we're not accounting for the water. Water is not aqueous, it's a liquid, right? So on the right-hand side, you only have 1. On the left-hand side, you had 5. Now, and our goal is to increase the concentration of all aqueous species. Would I shift to the left-hand side where I make 5 aqueous species, or would I shift to the right-hand side where I only make 1?
You would shift to the left.
Very good. And so what would happen to the color of this solution when I add water?
It would become more pink.
Very good, right? And that would blow your mind because you'd be like, okay, well, shouldn't it just become a lighter color of what it already is? That's what someone who doesn't know equilibrium would think. But now that you know the Chatelier's principle, you can predict this ahead of time. Very good. As you can see, Le Chatelier's principle is a prediction system. It'll tell you how reactions will change when stimuli are imposed upon them. Now, let me ask you this. Why are you learning Le Chatelier's principle? What do you think the use case of this is? Understanding what makes an equilibrium go left and what makes an equilibrium go right. Any ideas, guys? How is this applied in the real world? So the answer is pretty much every single material around you. If you look around you, you'll see plastics that are made from equilibrium reactions of polymerization. If you look around, if you see your car outside, your car is running on fuel, which arised from equilibrium reactions to produce it. When you look at cooking, when you look at any material you have, metals, the casing on your iPhone, the fertilizer that was used to make the rice in your cupboard, they were all using reversible reactions. And economically, we want to make the most product possible. So we will change temperature, we'll change pressure, we'll change volume in those chemical plants to maximize how much product we make, so we maximize the benefit to society. In the case of medicines, it's to increase drug development. In the case of fuels, it's to meet the transport requirements of society. In the case of ammonia gas, which is a very important equilibrium we'll talk about later, it feeds the world's population with fertilizer. So you don't realize this, but behind the scenes, the whole world is using, especially the chemical industry. Remember, chemistry is how you make everything. It's how you make the casing on your phone that uses anode reactions. It's how you make transistor chips, the materials you use to make that, right? All of that is grounded in chemistry, and all of that is grounded in LCP and understanding how to modify reactions. Okay, so it's very important and ingrained in, especially if those of you want to do engineering, those of you want to do medicine, it's a very important point because this is how your blood maintains its pH of about 7.35 at all times. It uses Le Chatelier's principle to counteract changes in acidity or basicity. It's quite interesting. And when that goes wrong, people die. So As long as you can start to appreciate some use cases of all of this stuff. All right, let's go to, this is a little bit too, you can do that later, we'll come across that answer. Actually, you know what, we'll do it. It's a little bit of a harder question because it's very exam hefty, but give it your best go. This is from the NEEP paper, which is one of the harder trial papers. Have a read of this. This is how they'll test you once you've mastered the content. So I'm pretty much putting you guys in hard mode and giving you a question. So don't be intimidated by this. We'll go through it together. Okay, once you've got an answer, hit the raise hand icon. So the answer is not too bad. The only issue is we've been introduced to the issue with exam questions. A lot of these exam questions are vague, and the answers, there's always going to be two options that you can quite confidently rule out. And with a harder exam question, there'll always be two options which are like, could be either, but what is the better answer, right? And we need to work through the process of elimination for all this. So you don't need to know the exact equation above. Does anyone vaguely remember what the equation was above? What happened?
I know it was endothermic.
Good. Okay. Yep. Anything else?
There was water on the right-hand side.
See, you don't need to know how to write this reaction word for word. In fact, all I would like you to write is probably cobalt plus chloride gives you cobalt chloride. Something along those lines, right? Maybe you can just write it as, let's go back up and see, how can we write it in the simplest possible format? Yeah, this simple format here. That's all I'd like you to know, right? Cobalt plus chloride gives you CoCl2. I just want you to know, since it was hydrated, water is also made, right? And the water came from being attached to this cobalt ion, right? So this is the reaction that you need to know. And there's heat on the left-hand side. Very good, right? You don't even need to memorize the colors. They'll tell you that, right? So point one, a few spatulas of hydrated cobalt chloride, right? So hydrated cobalt chloride is here. This ion solution, because when you add it to water, it dissolves, right? Is put in a test tube. The cobalt chloride is a pink solid, pink, right? The test tube was heated carefully, and the cobalt chloride gave off a vapor. What do we think that vapor was? Jacob?
I had a question. So it says that it was heated in an open test tube, but doesn't the system have to be closed?
When heated, put in a test tube, the cobalt chloride was a pink solution. When heated, cobalt chloride gave off a vapor. Yes, good question. So usually when we talk about equilibriums needing to be in a closed system, that's because most equilibriums will happen in a gaseous state, like in the Haber process, for example. And for that, you'd need a closed system. Otherwise, there'd be pressure-volume discrepancies. But do you agree in this system, there's not going to be a pressure-volume discrepancy because everything's a liquid, right? So it doesn't matter if you put a lid on it or you don't put a lid on it. The pressure is not going to affect the equilibrium, right? So this is a case where you can have the equilibrium occurring in an open system like a test tube. But if we were doing, for example, the Haber process, where nitrogen gas combined with ammonia, hydrogen gas to make ammonia, you can only do it in a closed system. Okay, good. So that was more a rule of thumb rather than a necessity.
Okay.
Good. Good question. All right. So with this, what is the vapor that was made, everyone? Logically think about it. If you heat something, you make a vapor, what would it be? Who's made pasta, spaghetti at home? When you heat up and boil the water, what's the vapor?
H2O.
Yeah, it's just H2O. So it's likely this vapor is just H2O. Remember, salt does not vaporize. Salt just crystallizes, and the solvent, remember, evaporation and crystallization will form the vapor. That's probably H2O, most likely, right? And it is H2O, but I'm just thinking as if I was a HSC student, that's what I would be thinking. Next is the solid was allowed to cool. When cooled, the remaining solid was blue. So what this is telling us is once we heated the solution and then let it cool, we went to the right-hand side or we made blue product, right? Now, let's say you didn't know whether this was endothermic or exothermic, but all the question told you was you had a reaction which, when heated, went to the right-hand side, right? A question that can commonly ask is a forward reaction exothermic or endothermic? And let's say you completely forgot whether this is endothermic or exothermic, because you're not needed to know that. How do we answer this question? Guys, what were the 3 questions I told you need to always ask yourself with any Le Chatelier's principle question? What are the 3 questions, Zainul?
Stimulus.
Yep.
Opposition and direction.
Very good, right? So fill it in, right? What was the stimulus?
Change to the right-hand side.
Was that the stimulus or the direction?
Direction. Oh, sorry, yeah.
You need to be very careful with answering those 3 questions. So what's the stimulus? So when heated, the system went to the right-hand side. Sorry, what did you say?
Temperature.
Okay, you identified the variable. You still haven't told me the stimulus. What happened to temperature? Did it go up or down? You need to be that specific.
Increase.
Good. When heated, the temperature went up. The reason that's so important is because when you talk about the opposite, you need to tell me what the exact opposite happened to temperature. If you just say temperature changed, you won't know what the opposite was, right? Good. And then finally, the direction is to the right-hand side. Okay. Now, when you increase temperature, the system will try to decrease temperature. How would it try to decrease temperature? By favoring the endothermic reaction or by favoring the exothermic reaction?
Exothermic.
Would it be endothermic?
Good, right? So no, the reason it's endothermic is when you increase temperature, you want to favor the reaction that's going to use up temperature.
Okay. Yep.
Right? So that's why you favor the endothermic reaction.
Yep.
Right? Good. So whenever we increase temperature, like the way I want you to think about it is endothermic uses up heat, right? Which is going to decrease temperature, and exothermic releases heat, which increases temperature. Okay? Good. Good. So stimulus is an increase in temperature, opposite is a decrease in temperature. So we're going to favor the endothermic reaction. And remember, our direction is the direction we go to achieve that opposite. So guess what we just found out, everyone? The right-hand side of the forward reaction is endothermic. So that's how you solve those questions. Do you see how we used those 3 questions but to solve a different question type? Good. Unrelated to this question, but that is a very common exam question they'll ask you. That's why I showed you how to think about it. Okay, good. Now, they said when the solid was cool, it became blue. So that's telling us that heating it shifted it to the right, as you saw with this explanation. Water was then added to the solid, and the solid became pink again, right? And then the test tube became warm. Does that align with our observations, everyone? What did we say? When we add water, we decrease the concentration of all aqueous species. So we're going to try making more aqueous species, aka we shift to the left, it becomes more pink. And what else do we make in the process? Heat, which they feel as warmth, right? So what is it showing you? Is it showing you just, so what can we cancel out straight away? And what do you think about C?
It is an ionic substance.
Good, but remember, the question is not always what's true, what's false. The question is, what should the student conclude?
So, well, they don't. Well, they can cancel out C.
Good, right? Because even though it's correct, that's not a logical conclusion a student can make just based on those observations. Based on those observations, what I as a student would be thinking is, I've put stuff in a test tube and it's changing color as I'm interfering with it. This is showing me something about the Chatelier principle. It's not telling me whether it's ionic, covalent network, covalent molecular, right? So C is correct factually, but it's wrong as a conclusion. It's not the best answer. What about D? Cobalt chloride decomposes when heated. Does it decompose when it's heated? What did we just say? When it's heated, it shifted to the right-hand side. Did it synthesize or decompose?
It synthesizes.
Yeah, very good, right? So that doesn't make much sense. Okay, and decompose is not the correct word to use, even if you're talking about the reverse reaction. That's called ionizing, right? So I would straight away have problems with that. Decomposition is when you get a solid and you break it down into two other salts. And a key example is calcium carbonate. When you heat it, it will decompose to calcium oxide, and you'll form a carbon dioxide, which you pick up with the lime water test. And finally, A and B. What's the better answer between A and B, everyone?
I'd say B.
Showing you a equilibrium reaction, and it's showing you a reversible reaction. Good. The reason why do we say it's B, Zainab? Can you explain it to the class?
Because for it to be an equilibrium reaction, most of the times it will be a reversible reaction. So it's just more like, just seems like more common sense to pick B.
Yeah, I'd say B is a better answer, because what you're seeing is you are seeing reversibility, right? You're seeing reactions going forward and backwards. So you're definitely seeing A. But what you're also seeing is once it was allowed to cool, or once water was added, it changed a color, and then it remained that color, right? So after step 3, if we didn't do step 4, the solution would have stayed blue, aka it would have formed an equilibrium, right? So I think it's also showing you an equilibrium reaction, or points where it is at equilibrium. So I'd say B is your best answer. A is correct. I think B is a better conclusion the student can make. Very good. So as you can see, exam questions are a bit of a different beast, but we'll get to those as we do more and more questions. Now next, iron nitrate and potassium thiocyanate. This is another example of a dynamic equilibrium. So for the first dot point, you learn 2 dynamic equilibriums, 2 static equilibriums. And question?
Yeah, I had a question from before. So you know how you said when you add or remove like solids or liquids, it doesn't change the concentration?
Yeah.
So then adding water, how did that change? Like, is that change?
So good question. Do you see how we wrote here? When we added water, water did not change the concentration of water. That's what we're trying to say. right? So adding a solid or liquid will not change the concentration of that solid or liquid.
Oh,
But
okay.
since everything else is aqueous, aka it's dissolved in water, what's the formula for concentration? What is it equal to, Anne?
N on V.
Very good. So if I add more water, the concentration of all aqueous species would change. So by adding water, I'm indirectly changing the concentration of everything else that is not a solid or liquid. Does that make sense?
Oh, okay. And if you
Yeah.
were to add a solid, would it change the
Wouldn't
concentration? Oh, okay. So
Wouldn't
only
change.
for water.
Only for water. This is a rare exception where adding a solid or liquid did change equilibrium, and it's only because everything else was dissolved in that liquid, right?
Okay.
If
Yeah.
I was to add, let's say there was magnesium solid too. If I added more magnesium, it's not going to do anything, right? As long as the magnesium doesn't dissolve. Like for example, if this was magnesium aqueous, and I added solid magnesium nitrate, then I would affect the equilibrium, because according to our understanding of chemistry, this is going to ionize and release magnesium ions. And they are going to go and increase this concentration. Does that make sense?
Yeah, that makes sense. Thank you.
Pretty much, if you cannot change the concentration of anything that is solid in the equilibrium, but you can add solids that will then change state and then affect things in an equilibrium, right? So just take it case by case.
Thank you.
Good, good. All right, next question. All right, this is a very important equilibrium because we're going to come back to this. I'm going to tell you right now, it's so important, it's in exam questions, and this might be in your end of term exam as well. So pay attention to this specific reaction. Iron nitrate and potassium thiocyanate. Now, this is another example of a dynamic equilibrium. You can see the iron 3 ions are a clear yellow color. Potassium thiocyanate, that's where the thiocyanate comes from. So you're going to be getting iron nitrate, and that's going to be giving you your iron ions. The reason we're not including nitrate is because it's not involved in this chemical equilibrium. We don't really care about the nitrate. The nitrate is just to make sure the iron ionizes and it doesn't precipitate, etc. The potassium, very similarly, is useless. It doesn't contribute at all to the equilibrium. It's the thiocyanate, which is this SCN. It's sulfur combined with the cyanide ion. What do we call it when multiple ions or multiple elements combine to form an ion that has a new collective charge? It's fixed. Its charge. NO3 minus, SO42 minus, what do we call those species? Jacob, what do you call those species? NO3 minus, SO42 minus, SO32 minus, what are they known as?
Polyatomic ions.
Very good. So the thiocyanate ion, SCN minus, is a prime example of a polyatomic ion. Very good. Now, what you can see is that iron 3 ions are going to combine with the thiocyanate to form a very distinctly colored metal ion solution. What do we call this? A distinctly colored metal ion combined to something else. What was that word starting with C?
Was it complex?
Very good. Whenever you see a colored metal ion in water, it has formed a complex. And that's all you need to know about complexes for now. Okay, in module 8, you'll learn much more about complexes. Okay, very good. Good. The last thing I want you to remember is that this forms a blood red color. Blood red. It's the iron combined to the thiocyanate, which gives you a blood red color. And you can see that right there, right? Good, good, good. Again, this is a colored equilibrium. So you'll see color changes as things are added and removed, etc. Okay, here this is an exothermic reaction. Again, guys, you do not need to know the enthalpy of any of these reactions. You do not need to know how to write it just yet, but hopefully by the end of this module with more and more practice you learn to, but they'll never ask you that directly. Right? You can always work it out from the question itself. Good. Now, let's say I'm going to write there the equilibrium. We'll do a couple of these questions, right? The rest will be homework, but I'll write it up for you. So iron 3 was combined with thiocyanate to form FeSCN 2+, right? Blood red. Okay, very quickly, question 1. Don't worry about giving me an exam answer to this. Just tell me which direction will the equilibrium would go. And just very briefly, why. Hit the raise hand icon once you've got an answer and I'll ask someone. Let's try doing this as fast as we can, this part. You can do the exam answers for homework. But as soon as you get an answer in what direction it goes, just hit the raise hand icon. Good. Good, Jacob. Good, Anne. Britannia? What direction would this... Oh, sorry. Let me reshare the screen again. Okay, Britannia, what's your answer for question 1? What are the answers to those 3 questions? Stimulus, opposite, and direction. Give it a go.
You're increasing concentration.
Yes.
So the opposite is decreasing concentration.
Of what? This is where you have to be very careful.
Oh, sorry.
What are you increasing the concentration of?
Of iron.
Good. Fe 3+. We need to be so accurate with the stimulus because the second we're not accurate, the rest of this question flow chart breaks down, right? This is the most important part of the 3 questions. Good. So the opposite is a decrease in concentration. So which direction will we go?
To the
We want to use
right
it up.
hand side.
Good. Go to the right hand side so we use it up. Very good, right? So the answer is RHS. Good. Next, let's go to Jacob. Question 2. Just tell me what stimulus, opposite, and direction.
So it'd be an increase in concentration of the thiocyanate,
Good.
and then opposite would just be a decrease in thiocyanate,
Good.
and then direction would shift to the right.
Very good. Perfect. All right. Okay. The effect of adding calcium fluoride. Now, what's going to happen here is when we add calcium fluoride, yeah, here you go. You can see in the method it says, fluoride precipitates with iron ions. What would happen when we add calcium fluoride as a result?
Oh, would it decrease the concentration then?
Good. And I'll give it a go for these 3 questions.
Oh, sorry, was that to me?
Yes, that's right. So we said that adding calcium fluoride, the fluoride will precipitate with iron.
Yeah, so if it precipitates with iron, it will decrease in concentration of the iron.
Good.
And the opposite would be to increase it. So that means it goes to the left-hand side.
Very good. Easy. Look, see, as you guys do more and more, it becomes very simple, especially when you break it down to those 3 questions, right? What I want you all to work on is writing it in a way to get full marks in all explained questions. If you can work on that in the next week. A little tip, if you go HSC NESA Chemistry additional questions, just search that up right now. There's an 80-page document with beginner chemistry questions to supplement you as you go through mod 5, 6, 7, and 8. Those are the easier level HSC style questions. I would recommend you do each and every one of those questions that are relevant to us now. So, as in not now, but over the next week, okay? There's questions about open and closed systems that were really good. There's a question about equilibrium. There's a graph question, which I really liked. Do those. They're a really good test of do you understand what's going on? Okay, good. Any questions? I think that's going to be it for today. So homework is going to be up till the end of page 37. Let me write this down. So I want you to complete.
Where do we submit the homework?
Yeah, so Zainul, I'm not sure if you were there at the beginning. So I was saying there's no point in you submitting homework, only because me giving you typed feedback is going to be, in honest terms, not good, right? Typed feedback, I think, is a waste of time. What you will need is to get verbal feedback from me on your answers, right? I think it's much more high value. So the goal is you'll be completing those questions, and at the start of next lesson, I'll be asking each and every one of you at random answers to some of these questions, and you'll be reading out that answer. And for the rest of them, I'll just very briefly tell you what you will need to say to get full marks. And if you had any questions about any of the homework questions, you bring it up at that beginning part of the lesson, and we go through it together as well. Okay? The goal is, as we go through this booklet, whatever page we end up at a lesson, you're going to be doing all the questions between the 2 page points in which we started the lesson and ended the lesson. That's the homework. And by the end of the 10 weeks, we should finish all 185 pages of this booklet. And you should have completed that, and also the trial questions at the very end. So if you go to the very bottom, let me just show you. Check this out, because I have so many trial questions. Look at the graphs they show you. They're not hard. They'll be challenging now because we haven't gone through the content, but what I mean to say is they will not be hard when we actually do them. And you can see that I just scrolled to the end and I straight away saw an exam question that's relevant to us, right? And do you see how they give you the equilibrium? Good, so start doing those as well. Jacob, question?
How do we get access to the answers for the trial questions?
Yeah, I'm going to be putting up all the papers for you. They're also on the website. So there's, if you go to www.edxlearning.online, there's, once you log in, you just need to let me know that you logged in, and then I can give you access to the student, enrolled student pages of the notes. But I think in the meantime, I'm just going to put up all the trial papers and upload to Google Drive. But for now, just sign into the edX Learning website. Let me know once you've done so, and I'll add you. If you go to my resources on the website.
Wait, do I just use my normal email?
Yeah, you can just use Gmail.
Okay.
And it works as long as it has your, as long as I know what your email is. Good. All right. On that note, I will see you all next week. Have a good week, and
All right. Thank you.
see you guys. Bye.
See ya.
Thank you.
Bye.
Sorry, can I just talk to you for a second?
Sure.
First of all, I'm so sorry I couldn't attend last week.
No, that's completely fine. Did you watch the recording? Do you know where to?
Yeah, I
view it?
did watch the recording. Yeah, I
Okay.
did.
Good.
And also my parents were wondering if you could take face-to-face lessons, like, once a month or so.
See, I would love to take face-to-face lessons with Anya. The only thing is, since I'm working at hospital and my shifts are erratic, it's very hard to give you all the time and place and then stick with it as well. It's very, because with a lot of last-minute changes that happen with hospitals, emergencies, and working full-time as well, it's very hard to fix one day to do so. What I can try doing is maybe once in the term we can try doing like a in-person class at a common area like UNSW, etc., which I'd love to do. It'll just be solely dependent on both of our availabilities, etc. Yeah.
Okay.
Yeah. No, look, I love face-to-face teaching because I get to see you guys understand the concept, make sense of it, and I can see you all grasping it. And it's easier for me as well because I can walk around. It's like I'm talking to you all. It's just very hard because of my workload and etc. Yeah.
That's okay. Yeah, that was all. Thank you so much.
No worries. Have a good week. I'll see you next week.
Too.
And how can I help?
Hi, I just had one question. For the homework, are we allowed to just do the SOD thing, or do you want like proper answer?
I would say this is solely dependent on you and how you feel, right?
Okay.
So if you think you're at that point where articulating exam-wise is not bad, stop doing it because there won't be much utility for it, right? But I'd say for the first couple of questions, until it becomes repetitive, I would be trying to answer it exam structured. And then once you got your structure, your template, and you can start saying it, and saying it sounds like an exam answer, then just start doing it as SOD.
Oh, okay. Thank you.
Good. No worries. Have a good week.
Bye, you too.